Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. Tonight, we turn our gaze towards something subtle, something that slipped into our view just long enough to leave behind a trail of questions, a visitor from between the stars, quiet, distant, and barely visible, yet stirring up a gentle storm of curiosity among those who watch the sky. The more we study it, the less we seem to understand it. Its name is 3I Atlas, the third confirmed interstellar object to pass through our solar system, and like a whisper in the dark, it arrived quietly, unannounced, unexpected, and wholly unfamiliar. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. Wherever you are, whether it's evening in the city or midnight beneath mountain stars, I'm glad you're here. Now, dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. We start with discovery, a moment so quiet you might not have noticed. It was late 2023 when a telescope on Mauna Loa, Hawaii, part of the Atlas survey, picked up a faint speck of light moving just slightly differently than the rest. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, a program designed not for deep cosmic mysteries but for catching threats, near-Earth asteroids, objects that might cross our planet's path. But sometimes, those same tools designed for defense stumble upon something far more poetic. 3I Atlas, short for the third interstellar object discovered by humans and named for the observatory that found it, was first catalogued as STUM 23A3. To most, that name says nothing, just letters and numbers. But to astronomers, those codes are soft breadcrumbs, a signal that something new had appeared in the sky. This object was faint, far fainter than most things we track. And its path wasn't quite right. Not elliptical, not closed. It wasn't orbiting the sun. Instead, it was sweeping in on a hyperbolic trajectory, like a skipping stone flung from another corner of the galaxy, just barely brushing the waters of our solar system before vanishing again. That's what makes it interstellar. It's not bound to our star. We know it didn't form here. We also know something else. By the time we noticed it, it was already on its way out. There's a quiet kind of tragedy in that. Imagine standing on a hill and seeing a figure in the distance, walking away into the mist. You didn't see where they came from. You'll never know where they go. But for a moment, you catch their silhouette, and that moment is all you'll ever have. Astronomers scrambled. They coordinated observatories around the world. They aimed telescopes, measured brightness, tried to infer rotation, texture, perhaps even composition. But 3I Atlas was faint. Even large ground-based observatories struggled to resolve it clearly, and still, it caught attention, not because of what it looked like, but because of where it came from. Its motion through space suggested a velocity and trajectory inconsistent with bound objects. There was no circular orbit, no cometary arc. This thing was diving in, slicing past us and leaving again. There was no second chance to catch it. We've only confirmed two such visitors before. One Oumuamua in 2017 and 2I Borisov in 2019. Both left mysteries in their wake. But Atlas might be more mysterious still. With each interstellar object we catch, we see just the briefest whisper of a much larger conversation. Something is happening out there in the void between stars. Something is hurling fragments and wanderers across light years. And now and then, one passes close enough for us to notice. We used to think such encounters would be rare, maybe once every few 100,000 years. But recent discoveries suggest otherwise. Maybe these visitors are far more common than we believed. Maybe our instruments are only now beginning to hear their footsteps. Even now, months after its detection, 3I Atlas is still being analysed. Its brightness, its path, its timing. Yet the more we study, the harder it is to say anything with certainty. No clear gas tail, no strong outgassing, no coma, not behaving like a comet, but not reflecting like a dry asteroid either. Not easy to define, not easy to classify. That's how our journey begins, with something real, something observed, and yet something still cloaked in questions. As we drift deeper into tonight's journey, we'll follow 3i Atlas along its silent path. Not to chase answers, but to marvel at the space between them. It's a strange thing, isn't it, to consider an object that doesn't belong, not in the rebellious sense, but in the quiet, cosmic way. 3i Atlas is such an object, a drifter, a visitor from beyond our solar system, and it's not the first. Before Atlas there was Oumuamua, the first interstellar object ever confirmed. Detected in 2017, it caught scientists entirely off guard. It came from the direction of Lyra, passed near the Sun, and then slipped away. No tail, no clear surface detail, just a slender, tumbling form. Oumuamua didn't behave like any comet or asteroid we knew, and because it was already leaving by the time we found it, most of what we learned came too late. We were left with strange acceleration data, theories of outgassing without gas, and whispers of artificial origin, though most scientists held that idea at gentle distance. Then came 2i Borisov 2 years later, a comet in every classical sense, icy, with a coma and tail, except for one crucial difference. Its speed and orbit revealed it wasn't bound to our star either. It had come from another system, another sun. So when 3i Atlas was discovered, many assumed it might be a new example in this growing pattern, another shard from beyond. But this one felt different. Unlike Borisov, it wasn't visibly shedding ice and vapour. Unlike Oumuamua, it didn't show the same extreme shape or strange acceleration, at least not in ways we could measure with confidence. And unlike both, it arrived quietly, slipping past our instruments for longer than expected. Its motion through space was precise in its strangeness. Most objects in our solar system move in ellipses. Comets swing in from distant reaches like sleepy messengers on predictable paths. But 3i Atlas moved on a hyperbolic arc, open-ended. That alone told us it was likely born beyond our sun's gravity, and yet it didn't quite move as expected. Its trajectory was hyperbolic, yes, but not wildly so. It wasn't speeding past in some dramatic flyby. Its velocity was just slightly beyond escape velocity, barely fast enough to break free from the sun's pull. This puzzled astronomers. If it came from another star, why was it moving so slowly, relatively speaking? Shouldn't it have more energy, more momentum after traversing interstellar space? Maybe it was tugged by our sun, slowed slightly, curving inward before arcing away again. Or maybe, perhaps, it was already moving slowly to begin with. But that raised another question. How does something drift between stars without getting swept up by stellar winds or ejected at far greater speeds? It's hard to imagine, but the space between stars isn't empty. It's filled with the faint breath of cosmic dust, the radiation of ancient explosions, and the soft gravitational tugs of everything nearby. Any object wandering there for millions of years would be buffeted ever so slightly. And yet, Atlas made it. We often think of interstellar space as hostile, and in many ways it is. But it's also deeply quiet, a hush that stretches for light years, a place where time flows slowly, and motion is almost undetectable. To survive such a journey, Atlas must be ancient, perhaps older than any planet in our solar system, perhaps formed near a star long gone cold, or perhaps just maybe it's not so old. Perhaps it was flung from its parent system recently, by a gravitational encounter, or by a dying sun shedding its outer layers. Astrophysicists still debate whether such low-velocity interstellar objects are common. Some argue they could be slowed by encounters with gas clouds, or nudged into slower paths by galactic tides. Others suggest our models underestimate the sheer variety of objects drifting between stars. Whatever the case, 3i Atlas became part of a very small club. We now live in an age where interstellar objects can be seen, not just imagined, not just inferred, seen, tracked, studied, even if only briefly. That's a monumental shift in our understanding of space. Just a few decades ago, such visitors were purely theoretical. It was assumed the odds of catching one at the right time with the right instruments were vanishingly small. Now we've seen 3 in less than 10 years. Could it be that the cosmos is more connected than we thought? That the vast gulfs between stars are not empty, but flowing gently with wayfarers like Atlas? It's a quiet thought. Somewhere out there in the deep silence there may be countless fragments drifting, remnants of systems we'll never see. Rocks, ice, dust, perhaps even the odd lost moon or core of a shattered planet. Atlas is one of them. And as we continue to refine our surveys, building ever more sensitive eyes on the sky, we might see more. But for now, 3i Atlas glides on, past the outer planets, toward the edge of the heliosphere, past the invisible boundary where the sun's breath fades into the general hum of interstellar space. It will keep going, and we will never see it again. A single brief meeting, then nothing but the data it leaves behind. Still, that glimpse reminds us, the universe is not static. It moves, it drifts, and it sends us occasional messengers, each carrying more questions than answers. As we continue drifting alongside 3i Atlas in our minds, we come to one of its most subtle, most perplexing qualities, the way it moves. Its path through our solar system is not just unfamiliar, it's deeply unsettling in its elegance. When scientists first charted its orbit, they saw something curious. Yes, it followed a hyperbolic path, which marks it as an interstellar visitor. But that path was narrow, almost balanced on the edge between escape and capture. It wasn't racing through our neighbourhood like a rogue comet fleeing a solar storm. It was gliding. That smooth arc led astronomers to ask, was this object merely passing through, or had something nudged it just enough to cross into our space? And even more puzzling, was its motion entirely natural? Usually, an object this small would be influenced mostly by gravity, the sun's pull, the occasional perturbation from a planet, especially giants like Jupiter or Saturn. But with Atlas, those influences couldn't fully explain what was being seen. There was something off. Its trajectory didn't quite match what pure Newtonian physics would predict. Of course, space is filled with complexities. Dust, radiation, gravitational subtleties. No model can perfectly account for every push and pull, but still, the numbers were just strange. We know that sunlight exerts pressure. It's gentle, so gentle you wouldn't feel it on your skin. But over time, and across vast distances, it can subtly shift small objects. If Atlas were light enough, it might be pushed by this pressure in detectable ways. But estimating its mass isn't simple. We don't know its exact size. We don't know its precise shape. We don't even know its spin or orientation. All we have is how it reflected light, and that light flickered. Its brightness wasn't constant. It fluctuated in patterns that hinted at an irregular shape. Maybe it was tumbling. Maybe its surface had patches of ice and rock reflecting differently as it turned. Or maybe, perhaps, it was being nudged in a way we couldn't yet explain. There are no known engines on it, of course. No signals, no transmissions, nothing to suggest machinery. But the motion still puzzled. With Oumuamua, something similar had happened. It sped up as it left the inner solar system. Not much, just a whisper of acceleration. But it was enough to break the models, enough to stir speculation. Was it outgassing? Was it venting ice in jets too faint to see? Or was it something we hadn't yet imagined? Atlas didn't display the same pronounced shift. But even subtle discrepancies in trajectory can raise quiet eyebrows. Astronomers tried adjusting their models, factoring in pressure from sunlight, exploring rotation scenarios, considering hypothetical gas emissions, but every explanation came with caveats. If it was venting gas, why was there no visible tail? If it was a fragile, icy body, why was it holding together so well near the sun? And if it wasn't outgassing, what else could explain the motion? Some suggested it might be porous, like a sponge, full of voids. Such a structure would make it lighter than expected for its size, and therefore more easily pushed by radiation. Others proposed it might have an unusually dark surface, absorbing more sunlight and warming asymmetrically. This could create small jets of gas even without the dramatic coma we associate with comets. But all of these remain guesses. Astrophysicists still debate whether Atlas's motion was truly anomalous, or just poorly measured due to its faintness. That's the trouble with shadows. When an object is barely visible, every calculation rests on light, and light can be deceptive. A dim flicker could mean a small dark object, or a large reflective one far away. Perspective becomes a dance between assumptions. Even with the best instruments, uncertainty reigns. So we're left with a quiet question. Did Atlas move strangely, or did we simply misunderstand what we saw? It's humbling to realize that even now, with space telescopes that can peer into galaxies billions of light years away, we can still be baffled by a rock the size of a mountain drifting past our doorstep. That is the nature of astronomy. A science of distance, of patience, of shadows and light. Sometimes it whispers more than it speaks, and in those whispers we find wonder. Atlas passed within reach, just close enough for our instruments to catch a few glimmers of reflected sunlight, just close enough to sketch a ghost of its path. But its story remains unfinished, because we don't know what it's made of. We don't know how fast it's spinning. We don't know whether its motion is ordinary or something else entirely. All we know is that it was here, and now it's gone. Still, for those few months in 2023 and 2024, it became one of the most mysterious objects in the solar system, not because of what it was, but because of how little we could say. The more we studied its motion, the more questions emerged. And that's where we find ourselves now, peering into the dark, chasing lines and angles and brightness curves, hoping they'll whisper the truth. Sometimes they do. Sometimes they only deepen the silence. Brightness is one of the few languages an object like 3i Atlas can speak, and even then it speaks in riddles. When astronomers first began tracking it in earnest, they noticed that Atlas did not shine consistently. Its light flickered, dimmed, and pulsed. Not like a beacon, but more like a heartbeat. This wasn't a trick of our instruments. The brightness truly changed. In astronomy, these light variations are called light curves. They are the soft signatures of rotation, of surface irregularities, of subtle eclipses when shadows fall across an object's face. For something like Atlas, these curves become clues. Perhaps, if we can understand the pattern of the flickering, we can infer the shape. A long cigar-like object might brighten and dim as it spins. A lumpy surface could reflect light unevenly. A fragment tumbling chaotically through space might produce strange asymmetric flashes. But the light curve of Atlas resisted easy interpretation. It didn't settle into a neat rhythm. It changed unpredictably, or too subtly to chart with confidence. Sometimes the object brightened more than expected. Other times it faded faster than models predicted. This lack of pattern made it difficult to say what kind of body Atlas really was. Was it a solid chunk of rock tumbling gently, or a looser aggregate, a cosmic snowball held together more by cohesion than by gravity? Astronomers ran simulations. They tried different shapes, different spin rates, even hypothetical compositions. Nothing fully matched, and as the object moved farther from Earth, the data grew thinner, the signals weaker, the variations smaller, harder to isolate from background noise. There's a kind of sadness in that. We were just beginning to ask the right questions when the sky began to go quiet. Still, the flickering light told us a few things. First, Atlas was likely irregular in shape. If it had been perfectly spherical, the light would have remained constant as it spun. Instead, it blinked and shifted, revealing facets, perhaps ridges, hollows, or jagged slopes. Second, it likely wasn't smooth. A smooth, uniform surface would reflect light evenly. The flickers hinted at roughness, maybe even variation in colour or albedo. And third, it might not have been rotating in a stable way. Some interstellar objects tumble, spinning on multiple axes, like a toy top winding down. Such motion could produce erratic light curves. Oumuamua, for instance, displayed similar behaviour. It tumbled end over end without a fixed spin axis. A chaotic, slow dance through the void. Maybe Atlas did the same, but with Atlas, the brightness changes weren't as dramatic. More subdued, whispered rather than sung. This made modelling even harder. Astronomers need clear signals to draw conclusions. With Atlas, the light was murky, the timing uncertain, the magnitude of change too small to pin down confidently. Still, there were moments, brief windows, when patterns seemed to emerge, perhaps a 6-hour rotation, perhaps a hint of elongation. But as with so much in astronomy, these may have been illusions. When you're peering across millions of kilometres, interpreting dim points of light, even the steadiest hand must doubt itself. Sometimes, 2 different models can explain the same data: a slow spin or a fast wobble, a dark object or a small bright one, a dusty surface or a thin, patchy layer of ice. And the light keeps flickering, refusing to choose. The sun plays a role too. As Atlas neared its closest point to the sun, called perihelion, it should have brightened. Solar heating would cause volatile materials to sublimate, creating a faint coma. But Atlas showed little sign of that. There was no pronounced tail, no sudden flare of brightness, just a steady dimness, like a shadow gliding across the sky. This deepened the mystery. Was it simply rocky with no ices left to evaporate? Or was it icy, but sealed beneath a crust too thick for sunlight to penetrate? Or, perhaps, it was shedding something after all, but at such low levels that our telescopes couldn't resolve it. There's a threshold in astronomy, the line between detectable and undetectable. It's thinner than you might think. Sometimes, an object may be just barely active, venting a whisper of vapour, losing a few particles at a time, but that activity can still affect its motion. A tiny outgassing event, invisible to us, might nudge the object ever so slightly. Could that have happened with Atlas? Some scientists think so. It might explain its odd trajectory. It might explain the faint, inconsistent brightening. Or maybe it was simply rotating unevenly, exposing fresher, brighter surfaces for brief moments before fading again. We don't know, and perhaps we never will. But there's a kind of peace in that. Not every question must have an answer. Sometimes the beauty is in the not knowing, in the flicker of starlight, in the whisper of a rock from another star, in the way its light played across our senses, then faded into the dark. The more we tried to fix its shape in our minds, the more it blurred, like a dream you try to remember just after waking. And yet, even that flickering light was enough to remind us, the cosmos is not still. It shimmers, it spins, and sometimes it surprises. In our quiet search to name 3 Atlas, we arrived at a fork. Was it a comet? Or was it an asteroid? Or could it be something that fits neither word well? On Earth, we like to label things. We like clear categories. Rocks or ice, comet or asteroid, this or that. But space often resists these boundaries. Traditionally, comets are icy bodies. Leftovers from the formation of solar systems, they spend most of their time in the cold reaches, far from their star. When they draw near to sunlight, they begin to sublimate. Their ices turn directly into gas, forming tails, ghostly veils of vapour and dust stretching millions of kilometres. Asteroids. on the other hand, are rocky, dry, solid fragments of planetary building blocks. They tend to orbit in more predictable paths, many gathering quietly in belts and clusters like cosmic fossils. When astronomers looked at 3i Atlas, they hoped it might behave like one or the other, but the more they watched, the harder it was to decide. At first, it showed no tail, no coma, nothing you'd expect from a comet. That seemed to suggest it was more like an asteroid, quiet, rocky, non-volatile. But then, as it neared the sun ever so slightly, its brightness fluctuated more than expected. Some hypothesized it might be shedding small amounts of gas or dust. If so, that would make it more comet-like. Still, no clear tail ever appeared, no dramatic flare of activity. Was it hiding its cometary nature beneath the crust? Or was it simply not icy at all? Some objects blur the line. We've seen comets that go dormant, icy at birth, but now quiet after countless orbits. Their surfaces become hardened, baked by the sun over time until the inner ices are sealed away. Could Atlas be such an object, only from another star system? Or maybe it formed in a different kind of environment entirely. Around other stars, the snow line, the distance from the star where ices can form, is different. A body born near a hot star might be rocky and dry. One born far from a cool star might be entirely icy. What if Atlas came from a system unlike ours? A binary star pair, perhaps, or a system filled with radiation, or one with an unusually dense disk of dust and gas during its youth. These differences could create objects that don't neatly match our expectations. Astrophysicists still debate whether we should use new categories for such visitors. Some have suggested terms like interstellar minor body or exoasteroid, but even these labels feel incomplete. Atlas might be part of a class we've never studied before, a fragment from a shattered moon, the crust of a lost planetesimal, a chunk of debris kicked out by a supernova long ago. It might be none of those things, or all of them at once. The challenge lies not only in what Atlas is, but in how little time we had to observe it. It approached, passed, and faded all within a narrow window. No spacecraft visited it. No long-term tracking was possible. We were left with only a whisper of light, a trail of trajectory, and a string of unanswered questions. Still, that whisper tells us something important. The universe is not made only of what we expect. There are worlds and fragments and frozen shadows out there that defy our neat little drawers and definitions, and Atlas is one of them. It doesn't seem to be a classical comet. It doesn't behave like a typical asteroid. It doesn't quite resemble anything we've catalogued in our solar system. It is, in its own quiet way, a reminder that we still know so little. And perhaps that's what makes it beautiful. Not because it fits into a pattern, but because it doesn't. Imagine standing on a quiet shoreline, seeing a strange piece of driftwood washed in from an ocean you've never crossed. You pick it up, examine its texture, wonder where it's from, but the tide pulls back, and you're left holding only a memory. Atlas is that driftwood, an object from the interstellar sea, carried by currents we cannot chart, shaped by forces we don't yet understand. Maybe in time we'll find others like it. Maybe we'll see patterns, build better models, learn what kinds of systems cast out such wanderers, but maybe not. Maybe Atlas will remain what it is, a singular mystery, whispering from the edge of our understanding, and in that space between what we know and what we guess, wonder blooms. In the quiet theatre of deep space, distance is the ultimate curtain. The farther an object drifts, the dimmer its story becomes, and with 3i Atlas, that curtain fell quickly. We never had the luxury of proximity. No spacecraft approached it. No flyby mission was dispatched. There was only earthbound observation, filtered through our planet's atmosphere, limited by the reach of our instruments. And Atlas was faint, so faint in fact that even some of our most sensitive telescopes struggled to track it for more than a few weeks. In astronomy, brightness is tied to distance and size, but also to reflectivity. or albedo. A small object with a shiny surface might appear brighter than a larger one made of charcoal black rock. With Atlas, we could only guess. Was it small and reflective, perhaps coated in ices, or large and dark, absorbing most of the sunlight it received? The truth likely lies somewhere in between. But whatever its actual size or reflectivity, one fact remained constant. It was getting farther away. As Atlas moved along its hyperbolic arc, it climbed away from the Sun, slipping into the outer solar system, beyond Mars, beyond Jupiter, drifting steadily into the deep cold beyond Saturn's reach. Every day its signal weakened. The angle grew less favourable, and then, almost imperceptibly, it passed beyond the grasp of most observatories. The silence that followed wasn't dramatic. It was gentle, the way a breeze fades after sunset, the way a shadow softens as night falls. That silence became part of the mystery, because with distance comes doubt, and with doubt comes imagination. In the brief period we had Atlas in our sights, astronomers scrambled to gather what data they could. The Very Large Telescope in Chile, Keck Observatory in Hawaii, Gemini North, each played its part. Each tried to extract a spectrum, light split into its component colours, revealing hints of what materials might be on the surface, but spectra require light, and Atlas offered only the faintest glow. Still, there were glimpses, a reddish tinge perhaps, a slight dip in brightness at certain wavelengths. Could this suggest organics, tholins? On other distant bodies, such as Pluto or Arakoth, these reddish hues are linked to complex organic molecules formed by radiation over billions of years. Could Atlas carry the same cosmic chemistry? Maybe. But the signals were faint. The margin of error was wide. Some researchers argued that the red colour was real, evidence of interstellar aging. Others cautioned against drawing conclusions from such low signal strength. Astrophysicists still debate whether the data tell us anything meaningful, and that's the difficulty with interstellar objects. They don't wait, they don't circle back, they don't allow for follow-up studies or second chances. Once they're gone, they're gone. With comets, we sometimes get decades to observe them as they swing back toward the Sun. With planets and moons, we can send missions, map surfaces, take samples, but Atlas was a visitor, a passerby, a whisper of another solar system glimpsed through fog. It's humbling and a little haunting. To know that we saw something born around another star drifting through our sky and then watched it vanish. Perhaps it now sails past the orbit of Neptune, past the Kuiper belt, into the realm of scattered disk objects and icy relics. Eventually it will cross the heliopause, the boundary where the solar wind slows and gives way to the interstellar medium. Out there, sunlight fades into memory. Temperatures plunge. Space becomes thick with nothing. And still, Atlas will drift. No propulsion, no destination. Just a silent momentum, gifted by some ancient upheaval long ago. Maybe it was ejected by a planet's gravity, or flung by the death throes of a collapsing star. Maybe it has been travelling for millions of years, or billions. If it carries ices, they'll remain frozen. If it carries secrets, they'll remain sealed. And unless some distant star captures it, pulls it into a new orbit, it will continue drifting forever. In some future age, another species might see it, catch its faint light, ask the same questions we now ask. What is it? Where did it come from? What stories might it hold? By then, we'll be long gone, but the questions will remain, because mystery travels well. It doesn't age, it simply changes hands. And Atlas, this faint, silent rock, has become part of that legacy, a fragment of the unknown offered to us for only a moment. We did what we could. We looked, we measured, we wondered, then we let it go. And now it moves beyond sight, beyond reach, but not beyond thought. For even now, long after it has vanished from our sky, we remember. and in that remembering, something beautiful lingers. Even in the quietest corners of the universe, instruments listen. They do not blink, they do not sleep, and among these ever-watchful machines, there are some designed specifically for catching what others miss. The Atlas system, the very network that first detected 3i Atlas, is one such watcher. Atlas stands for Asteroid Terrestrial Impact Last Alert System. Its purpose is pragmatic, to serve as Earth's early warning against potential asteroid collisions. It scans the sky for fast-moving objects, calculating their orbits, sounding the silent alarm when one appears too close for comfort. But sometimes, in its methodical sweep, it stumbles upon something unexpected, something like Atlas. The discovery wasn't dramatic, just a faint dot on a screen, a moving speck against the stillness of the starfield. But the trajectory didn't match any catalogued object, and that's when curiosity ignites. Follow-up observations poured in. Other surveys joined in. Pan-STARRS, Zwicky Transient Facility, even amateur astronomers with powerful backyard telescopes. Each one tracking, measuring, adding a brushstroke to the picture. In those first few days, the data was sparse. But one thing was clear. This object was not bound by the sun's gravity. Its velocity and path suggested an origin far beyond the edge of our solar system. This was no ordinary asteroid, no local wanderer. This was something else. Instruments like Atlas, while built to protect us, inadvertently become explorers. Their mission is defensive, but their gaze is wide, and that wide gaze allows for serendipity. The universe doesn't always send danger. It sometimes sends wonder. And systems like Atlas, designed for impact warnings, can instead offer glimpses into deep time and deep space. It's a reminder that the tools we build for one purpose often serve another, but detecting something is only the beginning. The real challenge comes next, trying to understand it. The observations gathered on Atlas were a patchwork of angles, times, and instruments. The object was already in motion when we noticed it, which meant we were forever catching up. Each telescope saw it from a slightly different vantage. Each used different filters, captured different wavelengths. Combining all of that into a coherent story is like assembling a puzzle in the dark. Pieces fit, but the picture remains cloudy. And yet, this is how astronomy often works. We rarely get perfect views. We collect shadows, echoes, glimmers, then we model, we simulate, we guess. Sometimes, those guesses get refined. Sometimes they fall apart. With 3i Atlas, the model struggled. Was it rotating on a fixed axis, or tumbling chaotically? Was it venting material, or simply being pushed by light? Was its shape elongated, flattened, irregular? The data refused to settle into one clear story. And that resistance, the object's unwillingness to yield to definition, only made it more fascinating. Instruments like Atlas, though powerful, have limits. They rely on reflected light, on line-of-sight motion, on brightness thresholds that can be easily muddied by distance and atmosphere. For faint, fast-moving targets like 3i Atlas, every detail must be wrung from tiny flickering signals, but even those signals are precious, because they add to a growing archive of interstellar visitors. First, Oumuamua, then Borisov, now Atlas, each discovered by wide-field surveys designed not for exploration but for vigilance, and yet each adding something profound to our understanding of what drifts between the stars. Perhaps most quietly astonishing is that, despite their limitations, these systems are seeing more than we expected. A decade ago, we thought interstellar objects would be once-in-a-lifetime discoveries, rare beyond rare. But now, with more eyes on the sky, we're starting to realize they may be common, not frequent in a human sense, but statistically frequent in a cosmic one. The space between stars, once thought to be empty and still, may be softly teeming with unbound debris, rocks, ice, dust, and maybe, someday, something more, something with structure, or signal, or purpose. Not yet, but maybe. That possibility, however distant, is why we watch, is why we build instruments that never sleep, why we scan the sky night after night, because you never know when the next messenger will appear, not from Earth, not from Mars, not even from our own sun, but from elsewhere, from some unknown cradle of formation far beyond the veil, and even if it fades too quickly for us to hold, its passing leaves an impression, an imprint in the data, a shimmer in the models, a question in the heart. We didn't design Atlas to find interstellar objects, but the cosmos doesn't ask for permission to surprise us, it simply does. Time in astronomy is a quiet thief. It slips past without footsteps, and before we know it, the object we were just beginning to understand has already faded. That's what happened with 3i Atlas. The moment we discovered it, we were already running out of time. It's a strange feeling to realize that you're meeting something only as it's leaving. Unlike planets or comets that return in graceful arcs, interstellar visitors do not circle back. Their paths are one way. Their presence is temporary, a brief chapter in an endless book. So with Atlas, there was a rush, not of urgency in the traditional sense, but of quiet focus. A gathering of eyes, of instruments, of questions, all knowing that their window was shrinking. Every night counted, every clear sky mattered, because each passing hour meant more distance, less light, and deeper uncertainty. Astronomers know this rhythm well. It's the rhythm of vanishing. A comet's tail may brighten and fade. A supernova may flare and then cool. A transient object blinks into the sky and then disappears. Atlas followed that same rhythm, though more quietly than most. There was no explosion, no dazzling display, just a soft passage through the sky, a dimming point of light receding into space. And as it moved farther, the questions deepened. Had we seen enough? Could we really say anything certain? Or would Atlas remain, like Oumuamua, a half-formed portrait? In truth, we may never know. That's the burden and beauty of astronomy. It teaches patience. It teaches humility. Because sometimes we only get one look, and in that look, we must gather all we can. The urgency that surrounded Atlas wasn't frantic. It was measured, focused, professional. But beneath that calm, there was also a sense of awe. Here was something from another star, a wanderer that had crossed unimaginable distances, perhaps carried for millions of years on a trajectory shaped by forces long since vanished. It didn't ask to be seen. It didn't signal its arrival. It simply passed by. And that passage, short, silent, incomplete, became enough. Time, as it always does, moved on. Atlas faded from view, the data slowed, the observations stopped, and we were left with only the record, pages of measurements, curves of brightness, coordinates plotted with care. That archive is precious, but it's also finite. Unlike stars or galaxies, which we can return to again and again, interstellar objects do not stay. That's why missions have been proposed to intercept future ones, missions that would launch quickly, perhaps using solar sails or gravity assists, to catch up with the next Atlas or Oumuamua before it vanishes. But those missions are still ideas, concepts. When Atlas came, we weren't ready. It came in silence, left in silence. But the echo lingers. It reminds us of the scale of space, of the distances that defy imagination. It reminds us of the fleeting nature of certain knowledge, and it reminds us that time in the universe flows at its own pace, slow, vast, and utterly beyond our control. We can only listen, and we did. Even as the light dimmed, even as the signal waned, we listened and we wondered. Perhaps that's all we were meant to do, because sometimes astronomy isn't about answers. It's about bearing witness. It's about standing still while something ancient and unknowable drifts past, and feeling that small flicker of connection. A reminder that we too are moving. We too are part of the larger drift. We may be bound to Earth for now, but our minds are not. They sail outward, chasing every faint glimmer, every silent trajectory. And as 3i Atlas slipped into the dark, we followed, not with rockets or probes, but with imagination. And with patience, because the next visitor will come, and next time we might be ready. Sometimes the faintest light carries the deepest meaning. For interstellar objects like 3i Atlas, light is more than brightness. It's a fingerprint, a whisper of composition, a hint of where something may have formed and what it may have once been. To uncover those hints, astronomers turn to spectroscopy, the science of splitting light into its constituent wavelengths. Much like a prism revealing rainbows, a spectroscope reveals the building blocks hidden inside a single beam of light. And for Atlas, this tool became one of our only bridges, because we could not touch it, could not land on it, could not fly beside it. But we could listen to its reflected starlight. And in that light, faint and flickering, there were signs, perhaps, of what it was made of. Initial observations hinted at a reddish hue, something shared with certain outer solar system bodies like Arakoth and some Kuiper belt objects. This red is often the result of complex carbon-rich molecules, tholins, that form when simple organic compounds are bombarded by radiation over millions or billions of years. Such coloration doesn't guarantee life or even complexity in the biological sense, but it does suggest time and exposure and slow chemical evolution in the silence between stars. If Atlas carried such compounds, it might mean it formed in a cold, distant region of its parent system, beyond the ice line, where radiation could sculpt its surface for eons. But spectroscopy is tricky when the object is faint. The signal-to-noise ratio becomes razor-thin. Small atmospheric disturbances on Earth, a passing cloud, or even the heat distortion from a telescope dome can blur the fragile data. So while some teams reported subtle dips and rises in Atlas's spectrum, potential hints of silicates, maybe carbon-rich material, others were more cautious. There was no single, unambiguous signature. No sharp absorption lines that told us here lies water or here lies methane. Just soft curves, gentle slopes, like trying to identify a melody from the echo of a single note. Still, those echoes matter, because they remind us the same ingredients found in our solar system, ices, organic, silicates, may be common across the galaxy. Perhaps these materials are not unique to Earth, or even to our Sun's family. Perhaps the raw stuff of planets, oceans, and maybe even life is scattered throughout the stars. Atlas becomes a kind of messenger in this hypothesis. Not a probe, not a craft, but a natural letter flung into the darkness, unreadable in full but bearing signs of the same cosmic ink. Of course, not everyone agrees on the spectral interpretation. Astrophysicists still debate whether the reddish tinge was real or just an artifact of observation. Some argue that we need more data, better models, more sensitive instruments, and they're right. But in the gentle mystery of Atlas, the absence of certainty is part of the charm. It forces us to ask better questions, to refine our tools, to remember that light, though fast, is fragile, and that the universe rarely reveals all its secrets in one beam. We do know this: Atlas was not metallic. Its spectrum showed no sign of iron-rich content. That alone rules out certain origins, like fragments from planetary cores or impact-forged debris. And it didn't show the deep ice features seen in active comets either. No sharp water absorption bands. Instead, it seemed dusty, possibly carbonaceous, perhaps coated in ancient residues that formed when it still orbited a different sun. Maybe that parent star has long since died, or maybe it still shines light years away, unaware that a tiny fragment of its past once passed through another system. and that fragment now fades, carrying its quiet chemistry into the void again. Spectroscopy, for all its limitations, gives us more than elements. It gives us connection. The knowledge that what we see in Atlas, the carbon, the dust, the patterns of aging, are not foreign, they're familiar. And in that familiarity we glimpse something cosmic, something unifying, that across unimaginable distance and time, matter behaves in predictable, knowable ways. The same physics that shape our solar system shape others. The same chemistry that makes up Earth's organics seems to decorate even the loneliest wanderers. Atlas may never reveal all of its secrets, but in the whisper of its reflected light, we hear a lullaby repeated across the galaxy, a song of dust and time, of silence and travel, of things born far away, but not so different after all. And as it drifts beyond reach, that song continues, quiet, incomplete, and beautiful. One of the most quietly fascinating questions about 3i Atlas is this. If it wasn't moving solely under the pull of gravity, what was nudging it? In the clockwork of celestial mechanics, gravity reigns supreme. It pulls planets into orbit, binds moons to their hosts, and commands comets on their long arcing journeys around the sun. But sometimes, something else joins the conversation, a softer force, one that's nearly invisible, yet undeniable over time. Light. Sunlight, to be exact. Photons may be massless, but they still carry momentum, and when they strike the surface of an object, especially a small one, they exert a tiny push. This effect is called radiation pressure, and over long distances and timescales, it can alter trajectories in subtle but measurable ways. For space dust, it's enough to change orbits entirely. For spacecraft, it's been harnessed deliberately, like in the case of Japan's Ikaros mission, which used a solar sail to drift through space, pushed gently by the sun. So with Atlas, astronomers asked, could its strange motion be explained not by propulsion, but by pressure? If it were small and light enough, say, porous, with a high surface area to mass ratio, it might respond to this invisible push more than a denser rock would. And perhaps that could explain some of the deviation in its path. But even that raised more questions, because the required surface to mass ratio would imply something highly unusual, an object far thinner, far more fragile than any asteroid we've seen before, something more like a sheet or a sail. When Oumuamua exhibited similar unexplained acceleration, some scientists like Harvard's Avi Loeb floated a controversial possibility. Maybe it wasn't natural. Maybe it was a fragment of alien technology, driven by light, intentionally or otherwise. With Atlas, such speculation was more muted. Its motion was less extreme. But still, the echoes remained. Could it be a natural light sail, a wafer-thin shard of an icy shell or volatile crust shed from a larger body long ago? Or was it simply porous, a fluffy aggregate of dust and ice loosely held together, what scientists sometimes call a rubble pile? Such bodies exist in our own solar system. Some comets and asteroids are little more than loosely bound clusters, barely surviving their own spin. If Atlas was like that, it might have reacted to radiation pressure more than a solid rock would. Another possibility lies in outgassing. If Atlas had pockets of volatile materials, ice trapped beneath a dusty surface, then as sunlight warmed it, small jets of gas might have escaped. These jets, even if invisible to our telescopes, could provide just enough thrust to alter its motion ever so slightly. We've seen this in many comets, but Atlas didn't have a visible coma, no tail, no dramatic brightening. If it was outgassing, it was doing so in whispers. Astrophysicists still debate whether these whispers were real. Some argue that the observed acceleration could be fully explained by modelling radiation pressure. Others suggest a combination of both pressure and low-level venting, but all agree, whatever was happening, it was subtle. And that subtlety is part of what makes interstellar objects so difficult to study. With no repeat passes, no future orbits, and no direct contact, we must piece together a story from breadcrumbs, a flicker in brightness, a deviation in path, a whisper of gas, and always a fading light. Still, the very idea that sunlight, something so gentle, could steer an object across the solar system is humbling. It reminds us of scale, of how in the vastness of space, even soft forces become powerful over time, and of how fragile things, dust, photons, distant rocks, can shape the grand choreography of the cosmos. In the end, 3i Atlas may be moving not because of engines or intentions, but simply because of light, because of heat and motion and the quiet push of photons dancing off its surface. And maybe that's enough, because it means the universe itself is shaping its path. No commands, no design, just physics, flowing gently like a river of light, steering a lonely traveller across the solar system and back into the night. And as we watched it drift, we glimpsed, if only for a moment, how delicately balanced the cosmos can be. In science, we build models to explain what we see. These models are not guesses, they're careful approximations grounded in observation and mathematics. We use them to predict comet paths, planetary orbits, even the spiraling dance of galaxies. And usually they serve as well. But sometimes, an object like 3i Atlas drifts through, and suddenly, the model doesn't fit. It's not that the math breaks. The math is sound. It's that the inputs resist classification. The assumptions don't hold. And in that quiet resistance, the mystery grows. When astronomers charted Atlas's trajectory, they applied everything they knew. Newton's laws. Solar radiation pressure, potential outgassing, rotational dynamics. But the results didn't add up cleanly. Some models predicted a slight deceleration. Others suggested a minor curve away from the expected path. Tiny deviations, but enough to matter. In orbital mechanics, even a shift of a few arc-seconds can translate to thousands of kilometers over time. That's why spacecraft must be guided with such care. So when Atlas didn't follow its predicted course precisely, scientists took notice. It wasn't alarming, it wasn't dangerous, but it was in its own soft way defiant. A reminder that our models, while powerful, are still incomplete, especially for visitors from beyond. Because our best models are tuned for objects born in our solar system. They assume materials common here, ices that melt at expected temperatures, dust that reflects in expected ways, rotation rates that fall within a familiar range. But Atlas wasn't from here, and so every input was an educated guess. Its mass, unknown, its density, estimated, its spin, inferred from flickering light, its shape, assumed. Put all of those into a model and even a small error compounds. So the fact that the path didn't line up exactly wasn't a failure, it was an invitation. To think differently, to question our templates, to ask, what if this object isn't like the ones we've catalogued? What if it's built differently, formed differently, ejected under stranger conditions? Astrophysicists still debate whether we're using the right reference frames for interstellar bodies. Our solar system sits within the Milky Way's gravitational well, influenced by tides, stellar encounters, and galactic drift. But objects like Atlas aren't simply passing through a flat plane. They may arrive with velocity inherited from another star's motion, so modelling their paths requires more than local gravity. It requires a broader map, a galactic one. That's where the models struggle most. Not because we lack intelligence, but because we lack information. A few weeks of tracking a dim point of light isn't much to work with, and when it leaves, it takes its secrets with it. The best models try to fill the silence. They simulate every scenario, a spinning oblong object, a fluffy, porous mass, a hard, icy core with surface dust. They adjust for the sun's pull, for Mars's passing gravity, for radiation, for invisible jets. But even then, uncertainty remains, and that uncertainty is humbling. because it reminds us that the universe is not a solved equation. It's a process, a conversation, a story still being written. Atlas is a chapter with missing lines, and in that silence we learn. We learn how easily our confidence can slip, how fragile even our best predictions are when the subject is unknown, and how important it is to keep watching, because the next interstellar object may tell us more, or it may confuse us further. Either way, the models will adapt, they always do, but first they must fail, and that failure, quiet though it is, opens the door to better understanding. It's easy to love astronomy for its grandeur, the swirling galaxies, the vast clouds of gas and dust, the brilliant births and deaths of stars. But there's something beautiful too, in the parts that don't fit, in the numbers that don't quite align, in the quiet rebellion of a fading speck of light that says, "I am not what you expected." That's what Atlas gave us. Not answers, but resistance. Not clarity, but curiosity. And in a world as vast as ours, maybe that's the most valuable gift. We are not strangers to interstellar visitors anymore. In the past decade alone, we've welcomed 3, Moai Oumuamua, the first, Tude Borisov, the most comet-like, and now 3i Atlas, quiet and strange in its own soft way. Though each arrived from the same vast beyond, their behaviours were startlingly different. Oumuamua appeared suddenly in 2017, a slender shard with no tail, no visible coma, and an unexpected acceleration as it exited our solar system. Some believed it was a rock, others wondered about exotic ices, a few whispered about alien probes, not as a declaration, but as a possibility born from scientific humility. Then came Borisov in 2019, more familiar, more cooperative. It behaved much like a classic comet, icy, active, shedding a tail as it neared the sun. Spectroscopy revealed cyanide, water and carbon-based compounds. In many ways, Borisov was a reassuring presence. Strange only because of where it came from, not what it did. And now, Atlas, an object that, again, breaks our neat little templates, neither clearly active nor entirely inert, reflective in ways we can't explain, accelerating slightly, but why? 3 visitors, 3 distinct personalities. What do they tell us? Perhaps that planetary systems across the galaxy form wildly different kinds of objects, or that our sampling is too small, too early to draw lines or categories. Still, there is a deep comfort in knowing we have started to see them, because for most of human history, these interstellar drifters would have passed unseen, untouched, unknowable, and now we've named them, measured them, watched them fade. Oumuamua came and went so quickly we barely had time to say hello. Borisov gave us more time, months to observe and study. Atlas gave us something quieter, a challenge to our understanding. It's tempting to compare them like siblings, as if their differences tell us something about their origins. Oumuamua seemed more asteroid-like, though its non-gravitational acceleration confused that image. Borisov was thoroughly cometary, shedding volatiles in a clear arc. Atlas sits somewhere in between. It has the brightness of a rocky object, but its path defies clean modelling. It didn't outgaze, but it didn't behave like a dead rock either. Perhaps we're beginning to see a continuum, a spectrum of objects ejected from other stars, some icy, some dusty, some fractured, some fused. And yet, that comparison also misses something important. Each of these visitors is a product not just of its composition, but of its journey. How long did it wander through interstellar space? What radiation did it endure? How many collisions did it survive? How much of itself did it lose before it reached us? We often think of these bodies as emissaries from other systems, but by the time they arrive, they are ghosts of their former selves, scarred, altered, silent. What we see is not the object that was born, but what remains after time and distance have done their work. With Atlas, perhaps we saw a survivor. Or maybe we saw something fragile and recent, a sliver flung from a young system, newly ejected, still fresh in its drift. Some scientists have even proposed that each interstellar object we observe may be unique not just in form but in story. Oumuamua, possibly the shard of a shattered exoplanet. Borisov, an ancient comet flung outward by a massive planet. Atlas, perhaps the crust of a volatile-rich body that failed to ignite. Astrophysicists still debate whether these interpretations hold water, but the very fact that we can ask the question is thrilling, because it means we're no longer alone with our solar system. We're beginning to receive samples, brief, uncatchable samples, from other neighbourhoods in the galaxy. No missions required, no rockets launched, just waiting and watching. With every interstellar object we catch, we gather not just data but context. We learn what is normal and what is rare, what is universal and what is peculiar, what might be shared across the stars and what might belong only to us. Atlas was another note in that growing melody. Its song is faint, its meaning uncertain. But it plays alongside those of Oumuamua and Borisov now, composing a harmony of interstellar drift. And as we hear more of these songs, we begin to understand that the galaxy is not a cold, empty space. It is a river, and it is full of floating things. How does something like 3i Atlas end up drifting between the stars? It's tempting to imagine it as a deliberate voyager, launched, aimed, and sent our way. But the truth, humbler and perhaps more poetic, is that it was likely cast out, not by intention, but by gravity. Planetary systems, especially in their youth, are chaotic places. Young stars form surrounded by swirling disks of gas, dust, and ice. From these disks, planets emerge, coalescing from grains into pebbles, into boulders, into embryonic worlds. And in those crowded nurseries, collisions are constant. Orbits shift, bodies scatter. Sometimes a planet flings a smaller body out of the system entirely. Sometimes a close encounter between two large objects sends a third on a one-way escape path, and just like that, an object becomes unbound, cast into the dark, no longer tethered to any sun. That's likely how Atlas began its journey, not as a traveller, but as a castaway. Perhaps it was once part of a young planetary system orbiting a small red star, or maybe a larger, hotter one. We'll never know for sure. But whatever its origin, it was flung from that place long ago. And that flinging likely came with speed, because to escape a star's gravity is no small feat. It requires either immense velocity or a series of perfectly timed gravitational slingshots. Once it escaped, it entered interstellar space, a region we often imagine as empty, but which is in truth filled with faint forces. There are galactic tides, subtle gravitational gradients caused by the structure of the Milky Way itself. These tides can stretch and scatter unbound objects over time. There are also stellar encounters, passing stars that, over millions of years, subtly tug on drifting debris, altering their courses with soft but persistent gravity. And then there are molecular clouds, dense pockets of gas and dust that can slow or deflect small objects, reshaping their paths across light years. Thrusius, just as Atlas, may have encountered any or all of these, each one leaving a fingerprint, each one altering its path if only slightly. The result, a trajectory that brought it one day into the sphere of our sun's influence. And for a brief time, we saw it. That's one of the most astonishing things about this entire story. This object, likely smaller than a modest mountain, moving without power or purpose, found its way here. Not because it aimed at us, not because we pulled it, but because the galaxy is dynamic. Alive with movement. Every star in the Milky Way orbits the galactic centre, including our sun. Every planet, asteroid, and grain of dust within those systems moves with them. Over time, stars pass close to one another. Debris from one system may fall toward another, and in rare moments, a fragment from an ancient collision, flung long ago, may find itself drifting into our skies. Atlas is a product of that cosmic dance. Perhaps it left its home system a billion years ago. Perhaps it passed near dozens of stars before reaching us. Perhaps it tumbled silently, changed only by radiation and time, and when it arrived, we almost missed it. That speaks to how many others must pass unseen, how many interstellar objects drift through our solar system, too faint, too fast, or too far to detect. Astrophysicists still debate how common such visitors might be. Some believe we may be seeing only a tiny fraction, that there are thousands, maybe millions, of unbound objects passing through the solar system every century, some large, some small, some like Oumuamua, some like Atlas, and some unlike anything we've imagined. Our instruments are getting better, surveys are growing faster, deeper, more sensitive, but we are still learning to listen. Still learning how to hear the soft footsteps of a drifting interstellar body, and every time we do, we learn something new, not just about the object, but about the galaxy itself. Because in studying Atlas's path, we don't just trace its motion, we trace the invisible hands that sent it here, the forces that shaped its journey, the encounters that nudged it across the void. In a way, it's a message not from one place, but from many, from all the stars it passed, from all the fields of gravity it crossed, from the chaos of birth to the silence of now, and we, for a brief moment, became part of its story, not as origin or destination, but as observers, as listeners, as the ones who noticed a faint light in the sky and paused quietly to wonder where it had come from. If 3i Atlas could leave a trail, not of light, but of silence, how many like it might be passing us now, unmarked? That question lingers in the minds of astronomers. For every interstellar object we detect, how many more escape notice? The truth is likely humbling, because our instruments, though powerful, see only a sliver of the sky at any given time. They're limited by resolution, sensitivity, and most of all, attention. And interstellar visitors like Atlas do not arrive with fanfare. They do not linger. They pass quickly, faintly, at odd angles. Most are too small, too dark, or too far to be noticed. They drift through the solar system without a whisper, never bright enough to register, never moving in quite the right direction to catch our gaze. This silent majority, those countless, invisible wanderers, may be the rule, not the exception. And if that's true, the cosmos around us is far more populated than we imagined. Not with civilizations or ships or signals, but with fragments, shards, cosmic seeds, born in distant star systems, cast out during planetary upheaval, and now floating endlessly. It's a staggering thought. At any given time, there may be dozens of interstellar objects moving through the solar system. Some barely larger than a pebble, some the size of buses or small buildings, and we see only the brightest, the nearest, the slowest. 3i Atlas was one of those rare exceptions, visible, if barely, and caught before it disappeared. It became the third confirmed interstellar object, but it will not be the last. Astrophysicists now believe the solar system is continually being pierced by these wanderers, like a lake, calm on the surface, but filled with unseen currents below. The upcoming Vera C. Rubin Observatory, with its massive mirror and wide-field camera, will help us listen better. It will scan the sky more completely, more often, and with far greater sensitivity than anything before it. And when it comes online, we may begin detecting dozens, perhaps hundreds of Atlas-like objects. Suddenly, what was once rare will become a pattern, and patterns lead to insight. We'll begin to understand how many of these bodies exist per cubic parsec of galactic volume. We'll learn their speeds, their compositions, their likely origins. Some might be icy, others rocky, some perhaps hollowed by cosmic rays or warped by stellar winds, and slowly we'll build a picture, not just of our solar system, but of all the places these objects once called home. because that's what they are in a way. Messages from other neighbourhoods, each one a small forgotten messenger, unconscious, unintentional, but rich with clues. We might find objects with materials we've never seen before, minerals that formed in pressures or temperatures unfamiliar to our world. We might even detect exotic isotopic ratios, hinting at the unique chemical histories of distant stars. And if one day we catch such an object early enough before it leaves while it's still approaching, we might even send a probe, a simple spacecraft. No need to land, just to fly close, to image, to analyze, to sample its dust. We would finally touch a piece of another solar system, a physical handshake between stars. That day has not yet come, but Atlas brings it closer, because every confirmed interstellar object strengthens the case for future missions. Every detection refines our surveys, every model improves our readiness, and every object like Atlas helps convince us of something quietly profound. We are not alone in the mechanics of planetary birth and death. All across the galaxy, other systems form and fragment, and the pieces, small, quiet, unfeeling, drift outward. Not toward us, just outward. But occasionally, by the grace of timing and emotion, one passes close, and for a moment we see it, and we remember that the universe is not static. It is in motion, constant motion. Even in the deep stillness of space, nothing is truly still. Everything is drifting, falling, swinging, dancing. And among those dancers are the silent ones, the ones like Atlas, unnoticed most of the time, but always there, waiting for the right light, the right angle, the right moment, to be seen, to remind us that the sky is not empty. What kind of place might have created 3i Atlas? To imagine its origin, we must leave behind our solar system entirely, float beyond the heliopause, beyond the familiar stars, and picture the kind of cosmic cradle that could give birth to such a silent traveller. Perhaps it formed near a young star glowing with newborn heat, its disk thick with gas and dust. In these swirling protoplanetary nurseries, planetesimals collide and clump. Moons are born, pulled close or flung wide. Gravity reshapes everything. Maybe Atlas was once part of such a system, a fragment of a forming world, never quite large enough to become a planet, but massive enough to remember heat, cold, and motion. Or perhaps it came from a system very unlike our own, one with a binary star, two suns locked in a gravitational embrace. In such places, the forces at play are more chaotic, more violent. A planet can be torn from one star and captured by another. Small bodies can be flung with astonishing speed. In those early turbulent epochs, it's common for systems to shed their outer layers, not just dust and gas, but solid fragments. Proto-comets, icy crusts, rocky cores. Some of those fragments fall inward, others are hurled out, forever. That may have been Atlas's fate. Perhaps it was caught in the gravitational wake of a forming gas giant, slingshotted outward during a brief encounter, or nudged gently but persistently by a migrating planet drifting inward toward its star. Or perhaps its parent star died. If Atlas came from an old system, maybe that system no longer exists as it once did. Maybe a red giant swelled, engulfed its inner planets, and scattered the outer bodies like ashes on the wind. Or maybe a close stellar encounter passed through that system. Another star brushing by, like ships in the night, its gravity tilting orbits, pulling debris out of alignment, ejecting some of it entirely. We know such encounters happen. In fact, our own sun may have passed near other stars during its early life, sharing material across gravitational boundaries. So maybe Atlas was one of those borrowed pieces, a sliver of another place, carried across light years by no force but motion itself. What would the chemistry of such a place be like? Would its elements match ours? Carbon, silicon, iron? Or would it carry traces of something older or rarer? We've already seen in meteorites on Earth that the building blocks of life, amino acids, sugars, complex organics, can form in the cold depths of space. If Atlas was forged in similar conditions, it might hold the same secrets. Not life itself, but the dusty seeds. Of course, we have no way to test this now. We did not sample it. We did not touch it. But the speculation is not idle. Because each interstellar object gives us a chance, not just to study a thing, but to dream of its past. To imagine the systems it passed, the stars it sailed near, the fields of cosmic dust it brushed against. And in that imagining, we begin to map a kind of galactic memory, not written in words, but in trajectories. Each visitor is a line, a motion, a vector from the unknown. And while we may never find its exact origin, we can ask, what kinds of systems produce objects like this? Are they common? Are they rare? Are we next? Because our own solar system too is ejecting matter. Long-period comets, those on massive looping orbits, sometimes pass near Jupiter or Saturn and are flung outward, beyond the sun's reach. These objects will not return. They become our gifts to the galaxy, and someday, perhaps, they will pass through other systems, faint lights in unfamiliar skies, watched by eyes not yet imagined, and perhaps, somewhere far away, someone will notice them and wonder, where did this come from? What star once held this? What story does this silent traveller carry? In that sense, Atlas is not just an object. It's part of a much larger cycle, a galactic dialogue, spoken not in language but in motion. We are beginning to listen. But more than that, we are beginning to understand that we too are participants. Our sun, our planets, our comets, they are part of this same cosmic scattering. And in time, the things we create, the probes we launch, the fragments we shed, may join the same chorus, bound for stars we will never see, carrying whispers of Earth through the darkness, just as Atlas, once long ago, began its own quiet journey toward us. To think that 3i Atlas might still carry ice beneath its quiet surface, beneath its silence, invites us to wonder how something so old could remain so well preserved. In interstellar space, conditions are perfect for preservation. Temperatures hover just above absolute zero. There is no atmosphere, no friction, no weathering forces like wind or rain. Only the occasional cosmic ray, the rare impact, and the constant slow bombardment of galactic radiation. It is the coldest kind of time. In that frigid stillness, ice can endure for eons. So if Atlas began its life as an icy object, perhaps like one of our solar system's comets, then there's a real possibility it still holds frozen materials, water, carbon dioxide, methane, ammonia, the usual suspects, but perhaps more exotic ices too, compounds we rarely see up close, nitriles, sulfur-bearing molecules, maybe even traces of complex organics. And if it's truly been drifting for millions or billions of years, those ices might bear the chemical fingerprints of a different kind of system. A system with different temperatures, different chemical ratios, different star types. That's what makes interstellar objects so scientifically tantalizing. They are samples, natural, uncontaminated samples of environments far beyond our current reach. The faint reddish hue detected on Atlas's surface may be a sign of space-weathered ice. In the Kuiper Belt and beyond, we've seen objects whose surfaces are coated in tholins, complex organic compounds formed when solar or cosmic radiation alters simple carbon-based molecules. These reddish coatings darken the surface and often signal that beneath the crust ices may remain. But here's the delicate balance. If the surface becomes too dark, it absorbs more sunlight and may slowly warm, sublimating its outer layers. If it remains highly reflective, it can preserve its internal cold more easily. Atlas's moderate reflectivity suggests it's somewhere in between. Not a perfect mirror, not a black sponge, something dusty perhaps, something crusted over. That leads to the possibility of a sealed surface, a thick hardened layer shielding interior ices. Such layers are common in long-period comets. As they orbit the Sun repeatedly, their outer shells thicken and insulate the core. If Atlas was ejected early from its system and never passed close to any star since, its surface may be less processed, more pristine. Or perhaps it once wandered close to another star, flared slightly and then cooled again. That could explain why it remained inactive even near our Sun. The heat it received during its brief passage wasn't enough to penetrate the crust, and so it drifted silently, its interior untouched. Astrophysicists still debate whether dormant interstellar comets are common. They may vastly outnumber the active ones, frozen relics that show no outward signs of life, but quietly hold the chemistry of their past. If so, then Atlas was one of many. One among a countless population of frozen emissaries, and yet we can't know for sure, not without sampling it. A flyby mission could have revealed so much. Even a single close image would have told us volumes, but Atlas came and went too quickly, and so we imagine, we model, we compare it to known bodies. Arakoth, the contact binary visited by New Horizons. Comet Bernardinelli-Bernstein, the massive long-period comet still inbound from the Oort cloud. The strange, red-tinged centaurs of the outer solar system. Each of these offers a mirror, a clue, but none are exactly like Atlas. Its trajectory, its faintness, its behaviour, all remain quietly unique. That uniqueness is both a scientific frustration and a poetic gift, because it reminds us that even as we find patterns, the cosmos continues to surprise us. Every object is a story, and some stories are never fully told. Still, we can dream. We can dream of one day catching one of these visitors in time, early enough to plan a mission, to observe up close, to taste its chemistry, to watch its ices flicker and fade as it nears the Sun. We might see crystals untouched for 1 billion years begin to sublime, releasing vapour into space. We might detect gases that tell us clearly, unambiguously, this is where it came from, this is what it's made of, and in that vapour we would glimpse not just a rock, but a history, a journey, a time capsule from another sun. Until then, we hold tightly to the silence Atlas left behind, and in that silence we hear possibility. Among the quietest questions stirred by 3i Atlas is also one of the most unsettling. What if it wasn't natural at all? Let's be clear. There is no evidence to suggest that Atlas was artificial. No signatures, no signals, no structure. It behaved, as far as we could tell, like a rock, or a fragment, or a remnant. But even still the possibility echoes, because whenever something behaves in a way we can't quite explain, especially when it comes from beyond the stars, the idea inevitably returns. What if it was built? That speculation rose most loudly with Oumuamua. Its shape, its sudden acceleration, its lack of outgassing. Each detail fed the idea that perhaps we were witnessing something engineered. A light sail, maybe. A shard of an abandoned probe. A relic adrift from another civilization's long-lost exploration. Some scientists pushed the idea forward, not as fact, but as hypothesis. A testable idea, worthy of consideration, if only to rule it out. Others dismissed it quickly, not from fear, but from caution. Science is slow, it requires restraint. And yet the door had been opened. So when Atlas appeared, with its peculiar motion, its absence of a clear tail, its uncertain composition, that door remained ajar. Could it be another fragment like Oumuamua? Could it be part of something larger, something broken, something shaped? Astrophysicists still debate whether we should even entertain the artificial hypothesis for interstellar objects. Most argue we should apply Occam's razor. assume the simplest explanation that fits the data, and natural explanations, however puzzling, still fit best. Radiation pressure, outgassing, unusual shape, fragile material. These can all explain the anomalies if we accept uncertainty, and yet, speculation has its place, especially in frontiers like this. Because even entertaining the artificial opens up important avenues. It pushes us to define what we would expect from a truly alien artifact. Would it reflect light in unnatural ways? Would it change velocity without an obvious cause? Would it tumble or spin or stay eerily stable? Would it radiate heat? Would it emit radio noise? And, perhaps most humbling, would we even recognize it? If an ancient probe, built by another civilization, passed through our solar system, would we know? Would it look like a spacecraft, or like a rock, or like something stranger still, something that defies all our categories? We might assume that technology must be symmetrical, metallic, geometric. But that assumption is deeply human. Nature itself is often asymmetric, irregular, eroded, shaped by function rather than form. A highly advanced probe might be built from biological materials, or cloaked in dust for protection. It might have no visible structure at all, or it might be entirely passive, drifting not to explore but to archive. If Atlas was such a thing, we'd have no way of knowing. No signals, no lights, no intentions. Just a silence we can't explain. That's not to say we should leap to conclusions. Science lives in caution, in slow inference. But it's worth asking, not to chase fantasy, but to stay open, because if we close that door too tightly, we may miss the very thing we seek. What we do know is this: Atlas followed a hyperbolic path. It came from outside the solar system. It did not orbit the sun. It was faint, fast, and quiet. Its trajectory didn't entirely align with gravitational predictions, and we couldn't definitively explain why. That doesn't mean alien, but it does mean unknown. And the unknown is the seed of curiosity, in a universe so vast where even the closest stars are lifetimes away. The odds of another civilization launching something, anything, that drifts far enough to pass through our solar system are low, but not zero. And the moment we accept that, we are changed. We become watchers not just of rocks and comets, but of possibility itself. We begin to ask better questions. We refine our instruments. We prepare, not just to discover, but to notice. Because maybe one day, something truly unusual will arrive, and maybe that thing will not be silent. Or maybe it will, and it will be up to us to listen differently. Atlas was most likely natural. A fragment of ice and dust, ejected long ago, shaped by time and radiation. But in studying it, we sharpened our eyes, and with each visitor we become just a little more ready for whatever the universe chooses to send next. It's a curious thing, how an object like 3i Atlas, so faint, so distant and so fleeting, can reveal the limits of everything we think we know. In a way, that may be its greatest gift. Because when a single rock from beyond the stars forces astronomers to revisit their assumptions, it becomes more than just a point of data. It becomes a kind of mirror, a mirror for science itself. We like to think of our understanding as expanding, and it is. We've sent spacecraft to the edge of the solar system. We've captured images of galaxies billions of light years away. We've listened to gravitational waves rippling through space-time. But every once in a while something small and quiet enters the frame and reminds us how much we still don't know. Atlas did that. It showed us that even now, with all our telescopes, all our models, and all our math, we can still be surprised. That's the kind of humility science needs to remain alive. For centuries we believed space was static. Then we discovered it's expanding. We thought comets always had tails. Then we saw ones that didn't. We thought interstellar objects were too rare to ever witness. Now we've seen 3 in less than a decade. So what else have we underestimated? Atlas humbles us not with grandeur, but with subtlety. Its brightness was barely measurable, its path barely noticeable, its spectrum barely readable, and yet it made headlines. It sparked debates. It inspired mission proposals, because in its mystery, it reminded us that the universe does not owe us clarity. We must earn it. And even then, there will always be haze at the edges. Astrophysicists still debate whether Atlas followed a clean gravitational arc or was nudged by something unseen. They question the precision of the observations, the modelling techniques, the assumptions built into our orbital simulations. They disagree, gently, on whether the object's reflectivity suggested dust or ice or weathered organics, and they wonder, privately perhaps, how many more Atlases we've missed. Because if we hadn't been watching just the right patch of sky on just the right day, we never would have known it passed. It would have been another unseen visitor slipping through the solar system like a sigh. That realization is both sobering and electrifying. It means the unknown is not far away. It's close, sometimes invisibly close, just waiting to be noticed. For science, that is a kind of sacred space, the boundary where knowledge meets uncertainty. That's where new ideas form. It's where missions are born, where papers are written, where students are inspired, and where astronomers night after night keep looking up, not to confirm what they already know, but to be surprised again. Atlas didn't tell us everything. But what it did reveal was this: we're just getting started. Our tools are improving. Our sky coverage is expanding. Soon, we'll detect interstellar objects not as they leave, but as they arrive. We'll track them in real time, study them up close, maybe even intercept one, and when we do, it will be thanks in part to the confusion Atlas left behind. Because confusion is fertile ground for progress. When models don't work, they're rewritten. When data resists interpretation, instruments are refined. When paths don't line up, we search for better maps. In that way, Atlas moved more than just through space. It moved our understanding forward. By showing us what we couldn't explain, it reminded us why we explore. Not for answers alone, but for the thrill of the question. If there's one thing the story of Three-Eye Atlas teaches us, it is this: astronomy is an act of patience. We did not capture Atlas with a spacecraft. We did not decode its full composition. We didn't even see it for long. And yet, the quiet flutter it caused in our instruments, in our theories, in our imaginations, remains. Because every mystery like Atlas becomes a seed. A reason to watch more carefully. A reason to build better tools. This is the quiet revolution happening in observational astronomy. We're preparing to wait patiently for the next flicker, and the one after that. The process has already begun. Surveys like Pan-STARRS and Zwicky Transient Facility are scanning the skies every night, looking for transients, brief, moving, vanishing things. In the near future, the Vera C. Rubin Observatory will come online. With its wide field and rapid cadence, it will be our best chance yet to spot faint interstellar objects as they enter the solar system, rather than when they're already on their way out. And we won't just detect them, we'll study them in real time, coordinate follow-up telescopes within hours, measure spectra while they're still near, even perhaps launch intercept missions. There are serious proposals for this now. Missions like the ESA's Comet interceptor, which will wait at a Lagrange point for a suitable fast-moving target, ready to launch on short notice. NASA has also explored designs for fast-response probes, not to catch up with an object after it's gone, but to meet it halfway, to fly alongside it, to take close images, to sniff its gases, to touch a story from another star. That level of preparation takes time, it takes funding, it takes belief, but Atlas helped fuel that belief, because even though we learned so little from it, the act of trying told us how much we cared to know. It revealed the edges of our current capabilities and inspired us to push beyond them. Astrophysicists still debate whether we'll ever see an object quite like it again, not because it was uniquely strange, but because it might have been uniquely visible. It may be that most interstellar objects are much smaller, much darker, much faster. Atlas may have been a lucky catch, a quiet reminder that timing matters. But even if we never see another Atlas, we are now watching in ways we weren't before. We are building systems that don't sleep, automated sky scanners that compare the night to the night before. They flag the faintest changes, track moving points, sound silent alerts when something drifts where it shouldn't. And because of that, the odds of catching future interstellar objects are growing. Maybe the next one will be brighter, slower, more cooperative, or maybe it will be stranger. Whatever it is, we'll be more ready. That's the quiet promise astronomy makes, that with enough patience the sky will tell us more. Not on our schedule, not with answers pre-written, but in its own time, through dim flickers and dusty trails, through paths that refuse to match, through light curves that confuse and inspire. We're entering an era where cosmic surprises will become routine, not because the universe has changed, but because we have. We're learning to notice, to be still, to wait, to respond when something crosses the edge of the known. Atlas may be gone now, vanished into the ink of the outer heliosphere, but it left us with something durable, the habit of curiosity, the readiness to act even when we don't understand, and the patience to let the sky unfold at its own pace. Because in astronomy, discovery is not a flash, it's a drift, a gathering of dots, a hush, a recognition, and that too is a kind of contact. We followed 3i Atlas through the sky, through the theories, through the limits of what we know and the soft shadows of what we don't. And now, as its trail fades from our view, we're left not with certainty, but with wonder, because perhaps that's what interstellar visitors do best. Not answer, but remind. Remind us how vast this universe is. Remind us that our solar system is not a sealed room, but a porous membrane, visited now and then by things born elsewhere, and remind us that the deeper we study, the more gently we must approach our questions. Atlas is gone now. It's likely past the orbit of Neptune. Moving beyond the Kuiper Belt, gliding past the scattered disk toward the edge of the sun's influence, it may still carry its ice, sealed beneath dust and time. It may still be tumbling slowly, silently, and eventually it will cross the heliopause, where solar wind meets the interstellar medium. From there, it returns to the place it knows best, the vast between. It won't remember us. It won't know it was seen, but we will remember it. Not because it dazzled us with light or sent us signals, but because it didn't. Because it arrived without noise. Because it left with questions. Because it whispered that we're part of something larger than ourselves. Astrophysicists still debate what it was, still refine the data, still model its motion with newer algorithms, and that's part of the process, because science doesn't stop when the object disappears. In many ways, that's when it begins. Atlas becomes a kind of canvas. Onto it we project our hypotheses, our tools, our hopes. It becomes a shared object, not just of data, but of meaning. And in its mystery we find momentum. It will take years, maybe decades, to understand just how much Atlas has taught us. Not in facts, but in habits. How to see differently. How to ask better questions. How to be ready next time, because there will be a next time. Another faint dot, another skewed path, another silence that doesn't quite match our models, and when that happens, we'll watch more closely. Maybe we'll send a probe, maybe we'll intercept a visitor before it slips away, maybe we'll bring back a sample, and maybe, just maybe, we'll hear a story never told before. Until then, we keep listening. We scan the sky not for noise but for stillness, not for answers but for openings. And through those openings something vast and beautiful drifts. It wears no name that we gave it. It follows no plan we made, but for a brief time it was part of our world, and that's enough. We don't need to explain everything, we only need to notice, and wonder, and wait. Now, as we let the echoes of Atlas settle, let's slow everything down. Let the stars fade to soft pinpricks in a deep velvet sky. Let the last curve of its trajectory vanish beyond the outer planets. Let your thoughts drift, weightless, just like that object did for eons. You might picture it now, dim, quiet, ancient, gliding between stars, untouched, unhurried. A tiny capsule of another place, passing silently through our solar system, then fading back into the dark. And maybe, in that image, there's comfort. Because the universe is not as empty as it once seemed. It's full of travellers, full of questions, full of quiet arrivals we may not even notice until they're already leaving. We don't always need to chase them. Sometimes it's enough to bear witness, to look up, to listen, and to know that even now as you rest, the sky's alive, drifting, shifting, sending secrets in the form of light, motion and shadow. So let the stillness settle over you now. Let the thoughts slow. Let the quiet take hold. The stars are still out there. The ancient light is still arriving, and the space between is never really silent. Thank you for wandering there with me tonight. Sleep deeply, breathe gently, and let the universe keep drifting by.